Hello, everyone, and welcome to Physics 13. This is Lab 4, which is going to be on moment of inertia. And also, we'll talk a little bit about conservation of angular momentum by looking at a demonstration of a student spinning in a chair that has bearings on it, so you can spin. Okay, so again, this is another one of those videos where I originally did a video lecture during the pandemic. So I will attach that right after this. I just want to let you know that there's a couple of differences. First of all, the lab numbering will be different. So this is lab 4 for this semester. On the video lecture that I recorded during the pandemic, I had to combine labs. So I believe it's called lab 1, either lab 1 or lab 2. So just be aware of that. There's a different numbering. And also the question numbering will be different. I think this was like the second half of that lab. So the questions might start at 9 or 10 or something like that. In this case, I just started them at 1. So make sure that you go by this semester's lab handout, right? If you're watching this because you need to review this particular lab, make sure you go by this semester's lab handout. The other thing that you'll notice is when you watch the video, in a lot of these tables, I have there's data collected, and that's because during the pandemic, students weren't able to collect data. So I had to pre-collect all the data, and that data will be in the tables. Okay, so you can either ignore it, you can get the data from your lab partners if you're making up a lab, or if you want, you could use that data. If you're making up this lab, if that's the reason why you're watching this video and you need some data, for some reason you can't get it from your lab partners, you could just use the data from the video, okay? All right, so what follows will be a discussion about moment of inertia and conservation of angular momentum. Great, thanks. Okay, so that's it for the circular motion part. The second experiment is going to deal with, again, we're going to look a little bit at moment of inertia and conservation of angular momentum. Okay, so first, a few things I need to define here. A rigid body, you can think of as any object, right, in which the atoms or the pieces of the object that make up the object are in fixed positions relative to one another. In other words, they don't move at all, right? So think like any solid object would be considered a rigid body. Okay, so that's the first definition. Moment of inertia. What is moment of inertia? Well, if I have some object here and I break it up into little bits of mass, right? So M1 is here, M2 is here, M3 is here, M4, M5, you break this whole thing up into little bits of mass all the way through Mn. I'm just showing 4 of them right now. And each little bit of mass is a certain distance away from the rotation point, the point at which you want to compute the moment of inertia about, right? Because it depends on what point you choose. So in this case, we're choosing this point right here. So M1 is R1 away from that point. M2 is R2 away. This is like its radius from that point. M3 is R3 away, and so on and so forth, all the way up to Mn, which is Rn away. Well, then the moment of inertia is defined to be the sum of each mass times its distance squared from the rotation point. Okay, let me jump on the iPad for a second to explain this a little bit further. Okay, so again, let's say we have this object. Let's say the axis of rotation we're going to choose, and we can choose any point we want to calculate the moment of inertia about. Let's say we choose this point right here as axis rotation. Then I can break this object up into little bits of mass. Like this is say M1, then let's say M2, M3, and so on, M4, all the way up to Mn. And each little bit of mass is a certain distance away from the rotation point, from the axis of rotation. I'll call this R1. This is R2. This is R3. This one would be R4. Rn. Okay, and again, you have to imagine that the whole thing is broken up into little bits of mass. And then if I want to compute the moment of inertia, which we call I, then this is simply going to be equal to m1 times r1 plus m2 times r2 squared plus, sorry, the radius is squared, plus m3 times r3 squared plus dot, dot, dot. And then you go all the way to the last one, which I'm calling mn times rn squared. But a more efficient way of writing this, since I'm summing all those things, I can write a sigma, right? Means sum. And the index goes from 1, so I equals 1 to n. And I can write this as mi ri squared. Okay, and then it has units, right? The moment inertia has units. Since it's a mass times a radius squared, it's going to be kilograms times meters squared. So the moment of inertia depends on the distribution of the mass about the point of rotation. Okay, so it depends on the distribution of the mass about the point of rotation. Here's an example. Let's say we have a ping pong paddle. So something like this. And so same paddle, right? So they have exactly the same mass. Wasn't drawn very well, but assume it's exactly the same shape, right? Same paddle. So same mass. But in this case, I calculate the moment inertia about this point in the handle. In this case, I calculate it about this point in the paddle itself. So for which case would I have a larger moment of inertia? Again, they have the same exact mass. It's just that the mass is distributed differently depending on what I choose as my axis of rotation. Well, hopefully you guys can see in this left-hand case, see how the mass is further away from that rotation point? And remember, to calculate moment of inertia, I'm using each little bit of mass times its distance squared, right, from the point of rotation. So if the mass is further away, that's going to lead to a larger moment of inertia, where in this case, the mass is closer to the rotation point. So I'm going to have a smaller moment of inertia. So I'll call this I1. In this case, I1 is going to be greater than I2. Okay, so it depends really on the distribution of mass about the point of rotation. Okay, another way to think about moment of inertia is we can look at Newton's second law. And in particular, we're going to look at Newton's second law defined for rotations. So I'll say for rotations. So first of all, let me do Newton's second law if we have a particle, right? Remember, that's F net is equal to mass times acceleration, right? F equals ma. Net force equals mass times acceleration. Well, it turns out there's an analogous formula that you guys will talk a lot about in lecture. You're going to learn about this in lecture, where there's an analogous term for force, for the net force. And you may already know this. It's called the torque. So we have the net torque is equal to, there's an analogous term for the acceleration. Instead of linear acceleration, we have what's called the angular acceleration, alpha. So net torque is kind of like your net force, but for rotations. Alpha is kind of like your A, right? Angular acceleration is like linear acceleration, but for rotations. So you might imagine there's something analogous to mass, but for rotations, and there is, and it is the moment of inertia. So I is analogous to mass. So it's kind of like, you can think of I as like a rotational mass. I'll say acts like a rotational mass. Whereas mass resists changes in linear motion, right? If you have a larger mass, it's harder to accelerate the object. A larger eye is going to resist changes in angular motion, right? So if you have a larger eye, it's harder to angularly accelerate. It's harder to rotate an object if you have a larger eye. So resist changes in angular motion. Okay, let me go back to the handout and go over a few more definitions. Okay, so again, we talked about the analogies between rotational form of Newton's second law and the linear translational form of Newton's second law. So this is the one you're most familiar with, right? The sum of the forces, the net force equals ma. And there's an analogous formula saying that the sum of the torques, the net torque, equals I times alpha. So I, again, is sort of like a rotational mass. It resists changes in angular motion. All right, a few more definitions. So actually, let me start with simple pendulum, because we've talked about this in the first semester, right? I mean, there's a couple of labs actually where we use a simple pendulum. Remember, a simple pendulum is simply a point mass that's at the end of a lightweight string or a lightweight rod. Okay, and in this lab, we're going to use a washer tied to washer tied to a string. That's going to be our simple pendulum. A physical pendulum is just some rigid body, right? So it can be any rigid body we want. It could be, in this lab, it'll be an aluminum stick. It could be like a baseball bat. It could be something that's just a solid object, right? That hangs from some rotation point, and it can oscillate back and forth about that rotation point. The period is the time it takes the pendulum to complete one oscillation. Okay, so it turns out that the period of a physical pendulum is given by this formula. So remember, T represents period. It's 2 times pi times the square root of the moment of inertia of that physical pendulum about the point of rotation, divided by the mass of the physical pendulum times g times d, where d is the distance from the axis of rotation to the center of mass. And then this one we already know, again, from our first semester, the period of a simple pendulum is simply equal to 2 pi times the square root of the length of the simple pendulum divided by g, right? It only depends on the length of the simple pendulum. Okay, so why am I mentioning all this? Well, we're going to use these ideas of the period of a pendulum and a simple pendulum to solve for the moment of inertia of that aluminum stick about certain points of rotation, about its axis of rotation. So we're going to use these ideas. How do we do that? Well, first, we have to know there's another term here. It's called an equivalent simple pendulum. This is simply a simple pendulum whose length is adjusted so that its period is the same as that of the physical pendulum. And again, if you watch my video, I recorded a quick little video on this showing you how I collected the data. You'll see I adjust the length of that simple pendulum, the length of the washer that's on the string, so that the washer and the aluminum stick oscillate with exactly the same period, right? So then the length of that simple pendulum is now called the equivalent simple pendulum because it has exactly the same period. So we're going to use that idea to solve for the moment of inertia of that aluminum stick. So how do we do that? Well, if they have the same period, right? If the period of the physical pendulum, which is the aluminum stick, is equal to the period of the simple pendulum, the washer on the string, I can set them equal. So here I set these equal. Basically, a little bit of algebra here. You're going to solve for I, solve for the moment of inertia. And you're going to find that I is going to equal the mass of the physical pendulum times d. Remember, that was a distance from the from the axis of rotation to the center of mass, times L, where L is the length of that equivalent simple pendulum. So it's just equal to mdl. So think of this I here as being our experimental moment of inertia. This is how we're going to find the moment of inertia of that aluminum stick experimentally, by using mdl. Okay, and then later, we're going to calculate the moment of inertia of the aluminum stick theoretically by using what's called the parallel axis theorem. So what does the parallel axis theorem say? Well, it says if you know the moment of inertia about the center of mass of the object, right? And I'm going to give you guys the moment inertia about the center of mass of the aluminum stick. So if you know about any object and you want to calculate the moment inertia, not about the center of mass, but about some new point, let's say this point right here, which is h away from the center of mass. By the way, h is really equivalent to what d was in the previous examples, but we're just calling it h now. So how do I calculate that new moment inertia about this new point? Well, it's going to be, so I want I now, the moment inertia about this new point. So the sub-zero means about this new point. It's going to be the moment inertia about the center of mass, plus we have to add this an additional term here, which involves h, and simply going to be the mass of the object. So the mass of that physical pendulum, the mass of the aluminum stick, times h squared. So the moment inertia about any new axis is always equal to the moment inertia about the center of mass plus mh squared, right? That's what the parallel axis theorem is saying. We can shift the axis of rotation from the center of mass to some new location if we add this additional term here. Okay, one more piece of terminology for the moment inertia stuff. There's something called the center of oscillation. And it says for every axis O that a physical pendulum oscillates about with some period, there exists another axis, O prime, about which the physical pendulum will oscillate with the same period. And the length of the equivalent simple pendulum defines the location of the center of oscillation from the original axis of rotation. So what this is saying is that we're going to look at the aluminum rod, right? And at first, we're going to rotate it about the end of the aluminum rod. So the axis of rotation is right at the end of the rod. And there's going to be some period, right? It has some period, oscillates back and forth. It turns out there's another location on the rod, and you're going to see this when you watch my little video. There's another hole that's towards the center. It's not exactly in the center, but I call it like a more central hole. And if you hang it from that more central hole, it oscillates, the aluminum stick will oscillate with exactly the same period. So that new location, that new hole is called the center of oscillation. Okay, it's actually like 2/3 of the distance from the end. Actually, here, let me go down and show you a picture of this. So we're going to rotate about the end point right here, right? And it's going to have a certain period. It's going to oscillate back and forth with a certain period. Then it turns out if I, instead of using this point as max rotation, I hook it up to this point right here. So you think of it right here. And now this part oscillates back and forth about this point. It'll have exactly the same period as the original one did when it was oscillating about the end. So this new hole, this more central hole here, is called the center of oscillation. Okay, and then the last thing that we want to look at in this lab is a little bit, at least qualitatively, look at angular momentum and conservation of angular momentum. So let me just briefly review what momentum is. And let me start with linear momentum first. So linear momentum of a particle with some mass or an object of mass m. Remember how this is defined, right? We usually call it p for linear momentum, and it's simply equal to the mass of the object times its velocity, right? And it had units of kilograms times meters per second. So that was linear momentum. Well, there's an analogous concept or idea, something called angular momentum. Usually we call it L. It's also a vector. Some books will use H instead of L, but in this case, we'll call it L. And we can kind of figure out this equation just by analogy again. If we think about like what's analogous to our linear quantities, but for angular. So what's analogous to linear velocity v, but for angles, it's going to be angular velocity, right? So the v sort of corresponds to our omega, which is really a vector, being careful. And remember the m, what does it correspond to in terms of rotations? It's the moment of inertia, right? So it's going to be I. And it has units of, actually it'll be kilograms times, let's see, I guess it'll be meters squared per second. Okay, now we talked about conservation of linear momentum, right, in the first semester. So remember, one way of writing Newton's second law in terms of linear momentum, we could say the net force was equal to the time rate of change of the total linear momentum. And again, if you haven't seen calculus, remember you could think of this as just as delta P total over delta T. And then the key thing we said, well, if the net force is 0, then that means the change in the total momentum, right, the change in total linear momentum was 0, which meant that the final linear momentum minus the initial linear momentum is equal to 0. And then of course we could bring one of those to the other side and we could say P total final was equal to P total initial. Okay, and that's what we meant by a linear momentum, total linear momentum was conserved. Okay, if the net force is 0, then total linear momentum was conserved. And since this is a vector equation, this could also just hold for one of the components, right? Maybe just the x component or just the y component could be conserved. Well, there's an analogous situation for rotations, right? So instead of F net equals the change in total linear momentum divided by time, we can say that the net torque equals the change in linear momentum. I'll say total linear momentum divided by time. So again, if you don't like the calculus, I'll write it as change in L total divided by delta T. So now we can say if the net torque is 0, then that means the change in the angular momentum is equal to 0. And then we could say that the total angular momentum final, so same argument as before, minus the total angular momentum initial is equal to 0. Or we could say that total angular momentum final is equal to total angular momentum initial. Okay, so it's the same type of reasoning that we use for the linear momentum, except now we're talking about rotations. So instead of a net force, we have a net torque. And if the net torque is 0, then angular momentum is conserved, right? The final angular momentum equals the initial angular momentum. And again, since this is a vector equation, this is true for each of its components. In our case, right, when we have the spinning chair, and you'll see this video when you look at the handout, it's spinning about the vertical axis, right, which I'm going to call the z-axis. So this equation, this conservation of angular momentum, is going to hold when we talk about just about the vertical axis, because that's the only thing that we're really interested in. So if Let me write that here. So in the lab, with the spinning chair, we have that the sum of the torques about the z-axis is equal to 0, right? So there's no torque applied about the vertical axis. Basically, what we're saying is that chair has really good bearings, so there's not a lot of friction. So we're going to assume that the net torque, or the sum of the torques about the vertical axis, is 0. So that means that the angular momentum about the z-axis, about the vertical axis, is conserved. Let's spell this better here. Another way of saying that is my LZ initial. So angular momentum about the vertical axis initial has to equal my LZ final. And remember, L is I times omega. So I can say like I initial omega initial, that's like my LZ initial, is equal to I final times omega final. And that's really what we're going to use in this lab. And I'm not going to do a lot with this. We're just going to kind of qualitatively talk about this. All right, great. Let me go back to the lab handout now. Okay, so on the iPad, right, I defined angular momentum. Remember, angular momentum, L is I times omega. And then we drew an analogy between conservation of linear momentum and conservation of angular momentum. And we said that for angular momentum, if the sum of the torques is 0, then the angular momentum is conserved. The L initial is equal to L final. And this occurs for any of its components. And really what we're interested in is the angular momentum about the vertical axis is going to be conserved. So I initial omega initial equals I final times omega final about the vertical axis. Okay, so for part A, again, make sure you watch this short video here on how I collected the data. This was the experiment involving the aluminum stick, okay? So first we hung the aluminum stick from the end. So we're going to calculate the moment inertia about the end first. We hung a simple pendulum, right, consisting of a light string and a washer from the same pivot point, right, from the end. And I adjusted the simple pendulum so that it became an equivalent simple pendulum, and both pendulums oscillated with the same period, right? So they had exactly the same period. And I found that the length of the equivalent simple pendulums when it had the same period was 66 centimeters. I measured its length. The length of the aluminum stick is a meter, so it's 100 centimeters. Okay, so question 15, your first question. Determine the ratio of the length of the simple pendulum to the length of the aluminum stick. The final answer should give the length of the equivalent simple pendulum L in term, like little l, in terms of the length of the aluminum stick, capital L. For example, if the length of the equivalent pendulum was 72 centimeters and the length of the aluminum stick was 100 centimeters, then little l is going to be 0.72 big L, right? Because you can think of it as, you know, the ratio of little l over large L is equal to 72 over 100. So little l is ultimately going to be 0.72 times big L. In our case, right, and you can see it here, instead of 0.72, what do you think you're going to use? Right, it should be 0.66. So you want to come up with that equation for the length of the equivalent simple pendulum. Okay, question 16. Now we're going to determine the experimental moment of inertia of the aluminum stick about its endpoint. And we're going to use that formula that we derived by setting the periods equal, right, of the physical pendulum, which is the aluminum stick, and the simple pendulum. Remember, the formula we derived was I, this is like I experimental, is the mass of the aluminum stick times d, which is the distance from the rotation point to the center of mass, times little l, which is the length of the equivalent simple pendulum. So we know that it's a uniform aluminum stick. So we know that the center of mass is right in the center. So the d here is going to be the length of that aluminum stick capital L over 2. And you don't even have to put in any values here. We're going to leave everything in terms of M and L. So capital M and capital L. So you're just going to leave it algebraically in terms of M and L. You don't have to put in 100 centimeters or 1 meter or anything like that. So simply you're going to plug into this formula, right? We have M, D is L over 2, and little l we found from above is going to be, I guess it'll be 0.66 times capital L, right? So you can plug all that in, and that will give you the experimental moment of inertia about the end point. Basically, it's going to be some decimal times ml squared. Okay, when you're finally done, there'll be some decimal times ml squared. Okay, question 17. So now what you do is you change the location of the axis of rotation. So now it's no longer rotating about the end, but now it's going to be rotating about the more central hole, right? Let me show you the picture here. So here was it rotating about the end. Now you're going to rotate about this more central hole. And you're going to find that it has exactly, so this is question 17, you should find that the aluminum stick has exactly the same period when oscillating about this more central hole. Therefore, that more central hole is called the center of oscillation. So now we wanted to determine the moment of inertia, the experimental moment of inertia about the more central hole using the same equation mdl. So the m is just capital M, just use M. D now is going to be different, right? Because remember, D is a distance from the axis of rotation to the center of mass. So that would be this distance right here. It's called H in the other example, but this is D right now. This is also D. So how do we find that? Well, you're told that the distance of that central hole from this end is 2/3 the length of the aluminum rod. So this is 2/3 L, 2/3 capital L. We know that the distance from the center of mass to this end is half of capital L, right? The length of the aluminum stick. So what is this distance D, which is also called H later on? Well, it must be 2/3 capital L minus 1/2 capital L, right? And that turns out, so 2/3 is the same as 4/6, 1/2 is the same as 3/6. So 4/6 minus 3/6 is 1/6 L. So it's just capital L over 6. That's going to be your D. And I have that right here. So D is L over 6. Okay, and then little l, so D has changed. Little l is the same as what you got from question 15 again, 0.66 capital L. So you're going to write that out. That's going to be your experimental moment of inertia about the more central hole. Okay, question 18. Now we want to calculate the moment of inertia theoretically. And how we're going to do that? We're going to use the parallel axis theorem to do that. So remember, the parallel axis theorem says that the moment of inertia about a particular point, let me go back to the picture here. So the moment of inertia about some new axis of rotation is the moment of inertia about the center of mass. So as if you calculated about the center of mass, and I'll give you that value, plus mh squared, where h is this distance from the center of mass to the new point that you want to calculate the moment of inertia about. So you have to add this mh squared to the moment of inertia about the center of mass. So when we calculate it about the end, right, it's going to be the moment of inertia about the center of mass. Well, what is that? I give that here. It's 1/12 ml squared. This basically comes from calculus. If you look this up in a physics book or an engineering book, you'll find that the moment inertia of a thin rod or thin stick about its center is 1/2 ml squared. H is really the same as D from before, right? It's the distance from the center of mass to the new point of rotation. Well, if we want to calculate about the end, then the H here is going to be 1/2 capital L. So now you have to solve for the moment inertia about this new point. It's going to be the moment inertia about the center of mass, 1/12 ml squared, plus m times h squared. So you have to plug in 1/2 L and square it, do a little bit of algebra, and you're going to find that the moment inertia is going to be some fraction times ml squared. Okay, and if you want, you can write that fraction as a decimal ultimately. Okay, then you're going to do the same thing, but now you're going to use the parallel axis theorem to calculate the theoretical moment inertia about the more central hole. So this hole right here. So again, it's the same formula. It'll be the moment inertia about the center of mass, which is 1/12 ml squared, plus mh squared. But h now is going to be the distance from the center of mass, that new axis of rotation. That's going to be L over 6. So you have m times L over 6 squared. You have to square that. You have to add the fractions. And again, ultimately, you're going to come up with some fraction times ml squared. Okay, so here's like the main table. This is the experimental moment inertia about the end. That's from question 16. Again, you're going to have a decimal value times ml squared. Here is the experimental moment inertia about the more central hole. So that's the one from question 17. Again, it's going to be some decimal value times ml squared. These are going to be the theoretical moments of inertia using the parallel axis theorem. So these are both from question 18. Again, about the end and then about the more central hole. So this is going to be some fraction times ml squared. If you want, you can write that fraction as a decimal. And how do you know if you're correct? These values should be very close. When you write it in decimal form, it'll be some decimal times ml squared, and they should be almost identical. And the same thing for these two. You should find that they're very, very close. So question 19 is to compare these two by computing a percent experimental error. So you're comparing the moments of inertia when calculated about the end point experimentally and theoretically. And then you're comparing the moments of inertia when calculated about the more central hole experimentally and theoretically by computing the percent experimental error. Make sure you show me all the calculations, right? That's important. Okay, and then the last part, and again, this is just sort of qualitatively, I don't want to do too much with this. This is the conservation of angular momentum demonstration with the spinning chair, okay? So imagine you have someone sitting in a chair, right? It's able to spin, and you're holding these 2-kilogram weights and you're holding them with your arms out, right? So your arms are out to the side. Someone gives you an initial angular speed. So you're rotating with some omega, right, in radians per second. And then you pull your hands in. So you pull those weights, pull your hands into towards the center of your body. What do you think is going to happen? Do you think you will spin faster, spin slower, or stay the same? Okay, so kind of predict what you think will happen in that situation, and then watch the video. This was recorded when I did this lecture. It was a bunch of years ago now, maybe 7, 8 years ago. And go to the part where the student is doing this experiment where they have the weights in their hand and they pull the weights in. So after watching the video, what did you find? Like, were your predictions correct or were they off? Just give me a couple sentences describing what you observed. Is that what you thought would happen or not based on your previous experience? Okay, question 21. Since angular momentum is conserved about the vertical axis, then we know that the initial angular momentum must equal the final angular momentum about the vertical axis. So I can say I initial, omega initial, remember that's the initial angular momentum, equals I final times omega final. So I want you to solve this for I final. So just algebraically solve this for I final. Just divide both sides by omega final. And you should find that I final is less than I initial. So when you pull your hands in, the moment inertia, right, when you pull your hands in, is smaller than the initial moment inertia when you had your hands out. Does that make sense? So just explain like whether that makes sense or not. Okay, and when you look at this equation, based on what you found on the omegas, you should see that I final is less than I initial. Okay, and then the last part is with the bicycle wheel. So again, you have to watch the video to see this, but originally the student is sitting in the chair and they're not rotating, they're still. The bicycle wheel is spinning. If you're looking from above, it's spinning counterclockwise. So it has and angular momentum that's directed upward, right? So this is the angular momentum of the wheel. So the angular momentum of the system is just due to the wheel initially. And it's going to be the moment of inertia of the wheel times the angular speed of the wheel. That's going to be the angular momentum of the wheel initially. And that's the angular momentum of the entire system. Then what happens is the student rotates the wheel away from them. So they rotate it through some angle theta. And it might be surprising, but you're going to see that the student and the chair are going to start to spin counterclockwise. Okay. So let me jump on the iPad one last time to describe the math behind this. And I just want you to really to sort of think about this. Okay, so again, because that chair has very good bearings and low friction, then we can assume that the net torque, or I'll say the sum of the torque about the vertical axis, I call it the z-axis, is 0. That means that the angular momentum about the z-axis is conserved. So if I do the angular momentum about the z-axis initial, that's got to equal the angular momentum about the z-axis final. And initially, the only thing that is spinning is the wheel. So the initial angular momentum is, I'll call it I naught omega naught. So this is the angular momentum due to the wheel. And then after, right, after the person rotates the wheel through some angle theta, it might be easier to draw. Here, let me draw this out a little bit. So this is before they rotate, and then after they rotate the wheel. So initially, the wheel's spinning, and it turns out angular momentum is a vector. It has a direction. And initially, if you curl your hand, your fingers in the direction of the spinning wheel, your thumb points in the direction of the angular momentum vector. And initially, it's just going to be directed upward. So this is like Li in the z-axis initially. I'll call it Lz initial. So this is like I naught omega naught in terms of its magnitude. And then after, they're going to rotate, the student rotates it through some angle theta. So this is theta here. The magnitude of the angular momentum of the wheel is still the same. It's still I naught omega naught. But now only part of that vector is in the vertical direction. Remember, we only care about what's happening with the angular momentum about the z-axis in the vertical direction. So what part of it is in the vertical direction? Well, it's this component, if I project that onto here. So now this is going to be I naught omega naught times cosine of the angle theta. But since it's conserved, right, in the vertical direction, there must be another piece, right? There must be another angular momentum of the system that I have to add to that so that I get back the original angular momentum vector. Like this vector plus this vector has to add to this, right? If it's conserved, because it has to be the same. So what is that additional angular momentum of the system? You'll find now that the student and chair are now rotating. So I'm going to call this I S for student, omega S. So now the student and chair have an angular momentum. So if we look at our formula here, initially it's just due to the wheel, right? I naught omega naught. And then finally, it's going to be, part of it will be due to the wheel. So I have to multiply by cosine theta, plus part of it is due to the student and chair. So what we can do now is we can solve this for the angular momentum of the student and chair. So I'm going to solve for this term. And you're going to find that basically I'm just subtracting I naught omega naught cosine theta from both sides. So the angular momentum of the student in chair equals, I'm going to factor out the angular momentum of the wheel. And this is going to be 1 minus cosine of theta. So this is like a key important equation here. So you see that the angular momentum of the student in chair depends on that angle theta, right? If theta is 0, then we know that cosine, so let's say theta was 0. Cosine of 0 is 1, and then 1 minus 1 is 0. So that means the angular momentum of the student in chair is 0 to begin with, right? It's not spinning. The only thing that's spinning is the wheel. But then when you rotate this, so when theta changes, it's going to affect this value right here. It's going to affect the angular momentum of the student in chair. So if we go back to the lab handout, okay, so back to the lab handout, question 22. I just explained all this to you, right? In fact, I even solved the equation for the angular momentum of the student in chair. So I student omega, like I called it IS omega S, right? Remember, it's going to be I naught omega naught times 1 minus cosine theta. So the only thing I want you guys to think about is for what value of theta does the angular momentum of the student in chair become a maximum? Okay, so think about that. And does this make sense based on what you observed in the video? So when you're watching the video, you'll see pretty clearly like when the student in chair are spinning the fastest. So what theta, what angle did they rotate the wheel through so that they were spinning the fastest? Okay, great. Hopefully that made sense. I know there was a lot of material in this lab. Again, if you guys have questions, please contact me if you have any questions about any of this. Great, thanks.